Now that we have formed our transistors and activated the implants and formed the nickel silicide, the next thing we do is essentially give this lot to the back end of the line guys, and then their job is to deposit all the interconnect layers and form the contacts and complete the rest of the process flow. So the first thing that the backend of the line process guys needs to do is to form a contact plug. That is how to contact these transistors that we just formed. So the first thing they do is they etch this hole into the oxide. So this was the oxide layer. So they etch this contact hole, and then the first layer they deposit is actually a titanium layer. So they deposit just a titanium layer over here. This titanium layer, the purpose of that, it's a gettering layer. So it getters all the oxygen that was left at the surface, or that the oxygen which was produced on the surface during this etch, and it helps in lowering the contact resistivity. Then the second layer they deposit is a conformal nitride layer. So they deposit a conformal nitride everywhere. And this nitride acts as a barrier material. So what this nitride does is it acts as a barrier material. So this nitride layer, it acts as a barrier. So whatever metal we fill over here, so if we want to, the metal that we fill is tungsten. So it prevents tungsten from diffusing it into the oxide. Also, tungsten uses this precursor, which is tungsten hexafluoride, so which has a high reactivity with both oxygen in the oxide and also with the titanium below. So this barrier layer essentially prevents that precursor from reacting with this oxide and the silicide, and also it prevents the metal from diffusing into the oxide. So once you deposit this tinitride layer, then you do a CVD deposition of tungsten. So this tungsten is a CVD deposition. It's a conformal CVD deposition. So it starts depositing from both sides, and then it starts growing, and you start filling it up with tungsten, and you fill it up from both the side walls, and you keep filling up until they meet in the middle. And there's often this seam formed because this it's a CVD process, so there's a seam formed in the tungsten. So these are the different process steps involved in making this tungsten plug. Let me show this in 3D. So the first thing we do is we start with our nice wafer that the front end of the line gave to us, and then we cover it with a photoresist. So it's covered with a photoresist, and then you pattern these holes. So you pattern these holes which will be acting as the contact plugs, and then you etch those holes into the oxide. So you etch those holes into the oxide, so you can see these holes which are etched into the oxide. The next thing you do is you fill it up with titanium over here. So you sputter a very thin layer of titanium, and then you deposit this tinitride seed. So this tinitride seed, either using a CVD or a ALD kind of a process, because you want it to be very conformal. So you deposit this conformal tinitride seed, and it fills everywhere. And then the next step you do is you do a CVD deposition of your tungsten. So the next thing you do is a CVD of your tungsten, which is your plug material. Again, it's a CVD process, so it grows from both the sidewall, and you can see it leaves this seam in the middle. And then the next thing you do is you polish it off. So you polish off this extra tungsten on the top. You also polish off this tinitride barrier layer, and what you are left with are these nice plugs which are now filled with tungsten. The next set of module in your back end of the line process flow, once you have done making the plugs, so once you have made these tungsten plugs which connect to your transistor, the next big module is making these interconnect lines, that is making these different levels of interconnect which route the signals between your different transistors, between your different cores in your microprocessors. So as I described to you earlier, a modern day microprocessor has anywhere between 9 to 10 levels of these interconnects. And the one which are at the very bottom, they are called as local interconnects because they run across short distances. So they just connect nearby transistors or nearby SRAM cells. The one at the very top are thick lines, and then they are called global interconnects, and they typically route the signals between different cores in your microprocessors. And the one in the middle are called intermediate levels of interconnects. And for all these levels of interconnect, the universal equation which determines the delay is that the delay for any of these levels of interconnect is proportional to the resistance of this metal line. So it's proportional to the resistance of this metal line, and it's also proportional to the capacitance. So it's proportional to the capacitance that this line has. So this line has with its adjacent line and what it has with the line at the top and the bottom. So if we need to minimize the delay, so one of the main requirements from the device guys or the circuit guys is to minimize the delay. So there are only two variables that we can play with. We can play to reduce the resistance of this line, and we can play to reduce the capacitance of this line. So let's look at how do we reduce the capacitance. So I want to look at from a material perspective how we can reduce this capacitance. The capacitance between these interconnect lines is can be described by this simple equation where it's proportional to the height and it's inversely proportional to the distance between these interconnects. So one thing we can play around is with the layout. So we can make these interconnects shorter, and we can separate them with more distance, and that's one way to change this influence this capacitance. But from a material perspective, what we can do is we can lower the K of the dielectric. So we can lower the K of the dielectric which is separating these two metal lines, and that is one way we can lower this capacitance. So there are multiple ways you can try to lowering the K. One way is to reduce the density of your silicon oxide. So silicon oxide is the lowest K material that we know. It has a dielectric constant or K of 3.9. So one way you can do is take this silicon oxide and try to make it porous, or try to reduce its density to reduce its K value. The other way it can be attempted is to reduce the polarization or reduce the density of this silicon oxide by incorporating other elements into it. So the one way we can lower, so the K value or the dielectric constant is proportional to the amount of it's proportional to the polarizability of the bond. So silicon oxygen has that bond is very polar. One way we can reduce the polarization is by introducing carbon. So the carbon oxygen bond has a much lower polarizability, and so one way is to reduce the K is that people introduce other elements into the silicon oxide. So they introduce fluorine, and that lowers that gives you some reduction in K. It reduces your K to 3.7. More importantly and more pervasively is what is used is you introduce these methyl groups, or you introduce carbon into your film, and that reduces your K value substantially. It reduces your K to 2.8, and that is also it's used pretty pervasively in the industry. Uh, the other way you can reduce the K is the ultimate way to reduce the K is to use air. So the silicon oxide, as I just described, has a K of 3.9 or 4. Air has a K or dielectric constant of 1. And people have what how they introduce this air in this back end of the line flow is by introducing these air gaps. And in one of the homework problems, we will discuss how the different ways we can introduce the air gap. But shown here is this picture. So these are the two metal lines, and you have an air gap between them. So this region is essentially air, and that reduces the capacitance between these two metal lines. And this is also used regularly in the industry, especially applications, chips involving memory such as flash. So it has a very regular pattern of lines. So it has a very regular patterns of lines, interconnect lines, bit lines and word lines. And air gaps is used routinely to reduce the capacitance between these metal lines, and also to reduce the capacitance between neighboring cells in a flash memory.